Okay, I just have this third video in this cubic polynomial series, and the whole purpose here is just simply, please excuse me, to show you these plots again from a different perspective, to give you some good insight as to how things are working here. Remember, we're plotting this cubic polynomial. It's the polynomial is just z cubed plus 9 equals 0, and we're trying to plot it so as to see where the roots are, to see that we have one real root, we have two complex roots that are complex complex conjugates of one another. So with that, let me show you this plot, and I think it's really pretty cool. We're plotting it with the Mac Grapher, which hopefully you will recognize that how powerful this is. I think it's one of the best kept secrets of the Macintosh, this Mac Grapher program. Okay, so my first plot, if you remember in a previous video, I took f of z and I wrote it as the real part of f of z plus the imaginary part of f of z. And I plotted those separately, and then I also took the magnitude of f of z. And I said where this magnitude of f of z is equal to 0 is where f of z is going to be equal to 0. So you can look at the zeros of the magnitude and tell where the roots are. Or you can look at where the real part crosses 0, and you can look at where the imaginary part of f of z crosses 0, and where they intersect will also be the location of the 0 points. So here first, let me plot out the real part. Okay, so here's the real part of the function. It's remember I said it's z cubed plus 9 equals 0. So this is the real part of that function. Okay, and you can see that there are places here where the real part is shooting up to infinity, here. There are places where the real part is shooting down towards negative infinity, okay, here and down here. And because of that, it's going to have to cross 0. And in particular, we look at here's our x-axis right here, and here's our y-axis. This is where z is equal to x plus iy. So you can imagine that this is probably crossing 0, let's say somewhere in this area. So you have, imagine you have a curve slicing right through the function where it crosses, where f of z is equal to 0. Curve slicing right through here, some kind of a curve, probably a parabolic shaped curve right in there. Okay, so this is the plot of the real part of f of z equals 0, and you can see that this will be crossing 0. Here's the vertical axis. Where does the vertical axis equal 0? It will be crossing there. Now let's look at separately at a plot of the imaginary part. Here's a plot of the imaginary part of f of z equals 0. It looks very similar. One difference is that the imaginary part sort of settles in down here very close to 0, whereas the real part was up above there, right? Remember, the real part is up here. That comes from the plus 9. And the imaginary parts settle down here, okay? So here again, we see that this imaginary part is going to there's going to be some sort of a curve in here where this thing crosses through 0. Okay, now as I've said, the function will be 0 when both the real and imaginary parts cross 0. So let me look at those two curves simultaneously. And here you see the curves simultaneously. It's really interesting. Here you can see the gap between the real part and the imaginary part right in there. This is because we're looking at z cubed plus 9, and the plus 9 is real, so that lifts up that real part there. And you can see that these two curves are intersecting. And you can see the along these lines right in here, okay? These lines right in there, they intersect. And it's where that intersection crosses 0, that's where the function f of z equals 0. So it's when both the real part and the imaginary part curves cross 0, where they both cross 0 together, is where the function is equal to 0. So what I have now done is I have taken the magnitude squared of the real part and the magnitude squared of the function, which is at each point it's the real part squared plus the imaginary part squared. That is what the magnitude of the function. It would be the square root of the real part squared plus the imaginary part squared. So let me plot that function right here. Let me take these two out. And this is what the magnitude of the function looks like. Here we have z cubed plus 9. And remember, as before, I was multiplying by a 0.1 here to sort of scale things nicely for us. So the magnitude squared never goes negative. The magnitude of any number never goes negative. The smallest it can get is 0. And you can see that it touches 0 at 3 places, here, here, and here. This 0 and this 0 are the complex conjugate zeros, and this is the real 0 right here. Okay, so if what I'm saying is true, then these points where this touches 0 have to be points where those where the two curves, the real curve and the imaginary curve, intersect, and they also cross 0. Well, here's the real curve. I think you can sort of see here what's happening there. This is coming down, getting very close to 0 right in there. So it looks like the real curve is in fact crossing through 0 at that, the way it should. And here is the imaginary plot. Again, you can see that it's coming down here. Looks like it's crossing through 0 right there. Okay, just like I said, it needs to be doing. Let's plot all three together, and we have this. So, that's pretty cool. So we have the intersecting lines between the real part and the imaginary part. You see these lines. Has to cross the point where the vertical axis equals 0, and here it's going to cross right, boom, right in there. So you see that it's where both of the real part and the imaginary part equal 0 together is going to be the location of the 0 of the complex valued polynomial. So I mean, these plots, I think, are certainly they're pretty. In fact, I mean, when mathematicians talk about the beauty of mathematics, you know, this would certainly fall within that category. I think it's really neat. It's a good illustration of first of all how the zeros of a polynomial are either real valued or form complex conjugate pairs, and it shows that when we have a complex valued polynomial, that you will have a 0 at those points where both the real part and the imaginary part of the polynomial are 0. And it shows you that we can identify those points on a graph if we plot the magnitude of the complex valued polynomial, as I've done here. And I did this all with the MacGrapher. Like I said, I think it's the Macintosh's best kept secret. So those of you who have Macs, use this MacGrapher, and if you don't, you need to find something like this that you can run on your computer, so you can do these kinds of things too. Okay, until next time.